Okay, today I want to talk a little bit about phase changes between the different phases of matter and then the gas laws that kind of come out of this idea that kinetic molecular theory said that everything is made up of particles and these particles are always in motion, and when we increase the temperature then we can increase the degree of freedom of how much these things are moving around. So we said, for instance, that solids are relatively fixed position in terms of their particles. They have a definite shape, they have a definite volume, but if we were to increase the temperature of that solid, then those particles would start moving around a little bit more and they'd have a little bit more freedom to move around. So I'd go from a solid to a liquid. And that phase change is, to give you the technical term for it, which is a term that you guys are comfortable and familiar with, is just melting. So a solid melts into liquid. I like to think about phase changes with water because we already know the terms for that. That's already a familiar thing for us. So we have this liquid now, whether it's water or whatever else, and the particles of a liquid, we said, are a little more free-flowing. They can move past each other. They have a little more freedom to move around than solids. And if you increase the temperature from there and go from a liquid to a gas, we call that evaporating. So if we're going from a solid to a liquid, liquid to a gas, then we're if we're going along this spectrum here, then in order to get from one phase to another, we have to put energy in, or rather we have to increase the temperature going this way. We have to increase the temperature. I'm just representing the increase in temperature with my arrow there going up, and then the T for temperature. Okay. Now if I go the other way, if I take a gas, for instance, you're in a hot shower and the steam comes out of your shower, and then you walk out of the shower after you've turned off the faucet or the spigot or your shower head, and then you come out into the rest of the bathroom and you find that the steam has turned into water on your mirror, right? Because the mirror is cooler than the air that was surrounding in your shower stall. So when you took away the temperature, when you removed energy, or when energy was released, then you went from a gas to a liquid, and that's called condensing or condensation. And again, we had to remove energy. Going from a gas to a liquid, energy had to be released, so we had to decrease the temperature and energy comes out. Now, that slows down the particles. We said there's this direct relationship between temperature and the speed and motion of the particles. So if we decrease the temperature, we're going to start slowing them down. They're going to start getting closer and closer together. They're going to start to get a little more dense, if you want to think about it that way, more closely packed. Then when we go from a liquid to a solid, okay, it's melting going from a solid to a liquid. It's freezing going from a liquid to a solid. Then we have to remove the temperature again. And again, that's a familiar term to us. We know that to freeze something, we have to make it colder. And on a particle level, on a particle scale, what that means is that we have to remove energy, or that energy has to be released in some way, shape, or form in order to get those particles more closely packed in the solid form. Okay, so these are our phase changes. I want to focus today, this lecture, on the gases, on the gas side of things. So I'm going to focus a little bit on what are called the gas laws, which come directly from kinetic molecular theory. So I'm going to start in with the gas laws here. I'm only going to focus on a couple of them. There's actually a number of different gas laws, and as you go on in your chemistry careers, you will learn about more detail for all of them. But I want to start with Boyles Law. Boyle's Law was discovered by a chemist by the name of Robert Boyle. Robert Boyle. He is one of the fathers of modern chemistry. There's a number of scientists that we can point to that were responsible for the shift from alchemy to chemistry, and Robert Boyle was one of them. And I'm going to talk in my next lecture about the rise of chemistry from alchemy, a little bit about him and some of the other fathers of chemistry. Now, Boyle's Law was looking at two particular characteristics of gases. He was looking at volume and pressure, and he was looking at the relationship between the two. So looking at volume and pressure. There's a number of different characteristics we can study about gases. Volume, how much space it takes up. Pressure, which is something we haven't really talked about much. Pressure is how much force is applied in a given area. So he was looking at how much that pressure would change if he changed the volume. Now, because we're scientists now, if we're changing two variables, or if we're changing one variable and looking at how the other one changes, then we have to keep other things the same so that we know that these two are the only ones that we're looking at. So in his experiments, he kept this at a constant temperature. I'm going to put just T for temperature there. And he also had a constant number of particles. Which means that he had a closed system. So he didn't add any gas to the system, he didn't take any gas away. So it's important to note what was kept the same so that when he was isolating these other two variables, he knew that he was just going to be looking at the effect that one had on another. And that's what Boyle's Law is all about. So in order to understand Boyle's Law, I like to use a piston kind of setup here. So if I have a piston that looks like this, so here's my plunger on my piston, and so this setup can move up and down. And if I have some gas particles in there, let's get my pink back out here. So if I have 10 gas particles in there, and I'm keeping this again at a constant temperature, then now if I change the position of this piston, I'm going to change how much space this gas has to take up. So let's say that I push that piston down, and now it looks something like this. Here's my new piston setup. So I've pushed the piston down to here. Again, I didn't change the number of gas particles I have, so I still have my 10 that are in there. And now what do you think happens to the pressure when I do that? So give that some thought. You make the volume smaller. What happens to the pressure? So I decreased my V for volume there. And hopefully you're thinking, all right, well, it has less space to move around in. That means these things are going to be knocking into the sides of the wall faster. They're going to be knocking into each other potentially faster. So you decrease the volume. That must increase the pressure that the gas is feeling. Okay? And you can think about it the other way too. If I was to pull out on this plunger and give the gas particles more space to move around in, then that would take off some of the pressure. Think about it like people too. If you have 10 people packed in a tiny space and then you put them in the same amount of people in half the size of the room, then that's going to increase the pressure and people's comfort level. But if you double the size of the room, if you make it bigger, then people are going to spread out, they're going to feel more comfortable, etc. So if you decrease the volume of your gas, you increase the pressure, and vice versa. I increase the volume, that means that the pressure goes down. Now, if one variable goes down, and that makes the other variable go up, we say that this is an inverse relationship. Inverse relationship, because as one thing changes in one direction, the other one will change in the opposite direction. And this is Boyle's Law in a nutshell. Again, we don't have a lot of math in this class, so we're really just thinking about this in a conceptual level. And Boyle's Law says that there's an inverse relationship or an inverse proportion between the volume of a gas and its pressure at a given temperature with the same number of gas particles. Okay, so that's Boyle's Law. If we go to our next chemist that discovered gases, we come to Jacques Charles and Charles' Law. Now, in the same way, there's kind of these four major characteristics of gases that we're looking at: volume and pressure, temperature, and number of particles. And so for Jacques Charles, what he was looking at the volume of the gas, so how much space it takes up, and what impact the temperature has on that. Now, if he's, again, only looking at two variables, then he has to be keeping two of them constant. So in his case, he's keeping a constant pressure now. I'm going to do P for pressure. And then also, just like with Boyle, a constant number of particles. Now, Jacques Charles was kind of an interesting guy. He, as many of the people that were studying gases at the time, was really interested in hot air balloons. And so when I think of Jacques Charles, I always think of hot air balloons. So you and I, we think about hot air balloons that look like this, right, with kind of an open end, and that's attached to a basket. Kind of looks like a light bulb the way that I drew it there. So there's the basket there. You have a heat source down here, which heats up the gas in the inside of the hot air balloon, and that allows it to expand, right? And the reason that I bring up hot air balloons with Jacques Charles is because he was the one who really came up with and formalized that relationship between temperature and volume. So when you increase that temperature, then that increases the motion and the speed of particles. That's kinetic molecular theory. And it will also expand the gas outward if we have the same number of particles and the same pressure. So as one goes up, the other one goes up. Now the opposite is also true. If I was going to decrease the temperature, make it lower, then the volume of gas would get smaller. So as the temperature goes down, the volume goes down. Okay. So Jacques Charles in his hot air balloons was kind of looking at, he wasn't just studying hot air balloons, but I like to mention hot air balloons with him just because of the relationship between the gases and the temperature there. So now this is different than what Boyle talked about. Boyle said as one variable went up, the other one went down. So this is as one goes up, the other one goes up, which is a direct relationship. And that's Charles' law. Charles' law says there's a direct relationship between temperature and volume given a constant pressure and a constant number of gas particles. So that's our second chemist there that studied gases. The third chemist is another one that's going to be important throughout the course of our quarter, and his name is Amedeo Avogadro. His real name is actually quite a bit longer than that, but we call him Amedeo Avogadro. He's an Italian chemist studying gases around the same time, and he formulated what is called Avogadro's law now. And so we've seen a law now that looks at volume and pressure. We've seen one that looks at volume and temperature, but we haven't really talked about changing up the number of gas particles, and that's what Avogadro did. He was looking at the number of gas particles. Whoops. And the volume of the gas. So he said, okay, at a given temperature, so we're going to keep the temperature constant, and a given pressure, so I'm going to keep a constant pressure as well. What he said ultimately is that equal volumes of gas will have equal number of gas particles. Equal volumes of gas will have an equal number of gas particles. This was pretty revolutionary because different gases have different chemical makeups, and at that time they didn't know all the details of that necessarily, but they did know that they were made up of different stuff, at least. And so this is an interesting revelation. This is an interesting relationship, that if you have an equal volume of any gas, that it will have the same number of gas particles at a constant temperature and pressure. Okay, and what we can kind of pull from that, if we're talking about these direct relationships then, is if you change the volume of gas, then you have to change the number of gas particles. Or rather, if you increase the number of gas particles, that will increase the volume of the gas. Or if you decrease the number of gas particles, then you have to decrease the volume of the gas. So it kind of looks like this. I'm going to use N for number of particles. And so when you increase N, you increase V. And vice versa. When you decrease the number of particles, you decrease the volume. So again, this looks a lot like what we saw in Jacques Charles's law. So this is a direct relationship as well. Now these three gas laws put together, Boyle's Law, Charles' Law, and Avogadro's Law, can all be combined into a gas law. And again, we'll get into more detail on this if you go on in your chemistry careers. But for what I would like you to know, they all combine together to form what is called the ideal gas law, which is one of those fundamental relationships. It's a scientific law that talks about the relationship between multiple phenomena. And so we're talking about pressure, volume. It's equal to the number of moles times some constant R times T. So here's our pressure, P for pressure, V for volume, N for number of moles, or number of particles. Remember in our SI unit video we talked about amount, talking about how much or how many of something there are, and we're talking about moles as our SI unit. So we could also think about this in terms of moles, but for right now let's talk about number of particles. R is a constant, which you don't have to worry too much about, and then T is temperature. So PV equals nRT, or PivNert, it is sometimes affectionately known. I want you to know this expression, PV equals nRT, because within it are the three different gas laws that we just saw. This inverse relationship between pressure and volume, and this direct relationship between volume and temperature, and pressure, and number of moles and volume. Okay. There are a couple more gas laws. There is one between pressure and temperature, and there's actually others beyond that as well. But for the ones that we're focusing on, those three are the ones that I want you to know. And they all culminate in the ideal gas law. Okay, if you have any questions on that, let me know. Otherwise, I'll talk to you again soon.